Hello, everyone. My name is Corey Whitney, and I'm going to talk to you about defining research priorities in complex agroforestry systems. I'm speaking today on behalf of my colleagues, Katja Schiffers and Eike Ludling as well. I'm very happy to deliver this content, and I think it's quite important and underutilized, the tools that I'll present, so I hope you get something out of this talk. Agroforestry systems are notoriously complex, and interventions to them are fraught with uncertainties. We care about uncertainty in our work, and we try to work with it and express it and communicate about it in supporting decisions. I'll use an example about informing agroforestry interventions in Vietnam. This is the paper by our colleague Hoa Do, if you want to learn or if you want to read more about it. So World Agroforestry Center, ICRAF, would like to roll out location-specific agroforestry inventions with many combinations of woody crops like coffee, mango, and tea, and timber like teak and acacia, with maize and forage grass as an alternative to maize monoculture on the steep slopes here in northern Vietnam. The models in this project were developed with local decision makers and stakeholders. These are complex enough to comprehensively describe these systems. This is a high-level sketch programmed to produce a net present value outcome based on the interventions. Just a high-level sketch. Of course, the real model is much more complex, but just to give you an overview here of how this works. And we could use this model to recommend which interventions would best suit the particular regions. And we grouped interventions by kind and compared them to standard maize monocultures. Net present values, these net present value outcomes were better with agroforestry systems with a higher net profit in the long term in coffee systems, in maize-based systems, and in simple systems. Agroforestry was characterized by a high initial investment and a time lag in terms of payoff. But our question was which, if any, of the many variables that we included in this model would be useful in better informing the best option. So we estimate these expected values based on our simulations, and we try to consider if we have enough evidence to make a recommendation, and if additional evidence will help us make a better decision. The choice is usually clear. If the overlap in outcomes from our simulations has a clear winner, then we can make a recommendation. However, we look at uncertainty because we want to know if we can do better. What if we're wrong, if we make the wrong recommendation? Again, here, this light blue is the maize monoculture. That's the baseline, that's the standard practice. And these other distributions are our interventions, agroforestry interventions. Do we need more evidence to make a recommendation? We're mainly concerned about uncertainty around the decision recommendation itself. We need to, the question is if we need to reduce that uncertainty in order to make a recommendation. Well, what type of evidence do we need and how much? And should we wait for that additional evidence, or should we go ahead with the current recommendation? These are all our main questions regarding this decision support. So one useful output of the decision approach is the calculation of expected value of perfect information, or EVPI. It can help us identify those variables for which more information would maximize the model output. EVPI is the expected value given perfect information before decision making minus the expected maximum value. I'll tell you how that works now. We use the example of a market investment. So what is the gain of an investment option given these different possible future market states? Should we choose to invest or not to invest? Not investing, keeping the money in bonds, for example, always has a small win. Here we simulate with 500, small win of 500. We multiply these by the different projected possible states of the future market to calculate the expected value of not investing. Here you see 20% times 500 plus 30% times 500 plus 50% times 500 means 500 for the expected value of not investing. Investing in the riskier stock option has different outcomes in the different states of the future market, but it's still the expected maximum value. We use the same process for calculating, but it's higher here. We can expect to earn more overall if we choose that option. On average, we should earn more. The expected value of the decision given perfect information, or EVPI, expected value given perfect information, is calculated as the sum of all the best options, always making the more gainful choice. As with others, these outcomes are multiplied by the respective probabilities. So the same formula, same calculation, and we get the expected value given perfect information if we always made the best choice in each situation. So that is equal to 260. It means that knowing the direction the market will go, or having perfect information, should be worth 260 euros to us. EVPI can be useful for defining research priorities. It quantifies the potential gain in the units of an output variable, given accurate knowledge on the value that an input variable will take. When the output variable is monetary, the EVPI can be interpreted as the highest price that a decision maker should be willing to pay for perfect information, but it doesn't have to be monetary. Generally, we calculate EVPI with continuous probability distributions. Here we provide an example of an agricultural decision to apply fertilizer and the effect on yield given the soil nutrient content. We assume that the nutrient content of the soil will follow a normal distribution and that the additional gain in yield under the decision not to apply fertilizer will remain constant. That's the green line. Therefore, the expected gain for the decision to not apply fertilizer is simply 0. When applying fertilizer, the effect on additional gain is negatively correlated with the nutrient content of the soil. So at a certain level, it causes losses in yield due to toxic effects. This is this dashed red line here. To calculate the expected gain in yield when applying fertilizer, we multiply that dashed red line with the normal density distribution, similar to multiplying the gains and losses with the probability of the market going in the respective directions in the previous example. And for the resulting weighted response, this red line, we add up the areas under the curve, A and A minus B. As the positive part A is greater than the negative part, the expected value of applying fertilizer has a small positive value. Therefore, applying fertilizer is the decision with the expected maximum value. And the expected value given perfect information is equal to A in this case, i.e. to apply fertilizer in low nutrient and not to do that in the high nutrient condition. And EVPI is then again calculated as the difference between the expected value of given perfect information and minus the expected maximum value, or that difference between EVPI and EV given PI and EMV. So knowing the nutrient content of the soil before deciding whether to apply fertilizer or not would increase the yield by an integral over, or the area of A in this case. So back to our example from Vietnam, the discount rate of the farmers was consistently important for a factor right across the simulations. Due to the long time frame of agroforestry practices, which can take several years to begin producing substantial benefits. Farmers have a strong preference for, let me just open that here. So farmers have a strong preference for the present day net benefits over future benefits, and they value present payoffs much more highly than long-term profits in their decision-making. Another high value variable was yield at peak. We have uncertainty about what the expected yield will be, and more certainty about this could help us be more confident in decision support. But neither of these justified much of an investment, under 500 US dollars in this case, meaning that we were certain enough without needing to make further measurements. So how can we apply this? Well, we built these formulas into our decision support package in the R programming language. We built in functions, including the empirical EVPI and multi-EVPI. The empirical EVPI does the calculation much like the one we just saw, but the files and vignettes will help walk you through the process in the R package. And So really using value of information can help us focus our research efforts, can highlight critical uncertainties, determine whether additional information could increase confidence about the emerging decision recommendation, and it can be used for prioritizing knowledge gaps that should most urgently be narrowed in order to improve certainty about the decision. This is how you find us, my co-authors and I, and thank you very much.